Learning Task 1.1. Question number 5 of problem set 1.3. Use Dixon's and Grubbs methods to test for outliers and water harness data in problem 1. The given data set for problem number 1 are 8.02, 7.84, 7.98, 7.95, 8.01, 8.07, and 7.89. Arranging from smallest to largest, the dataset are now 7.84, 7.89, 7.95, 7.98, 8.01, 8.02, and 8.07. For Dixon's method, we will be using Q-test. The equation used for Q-test are the following. For Q1, the numerator is the difference between the second number and the first number, while the denominator is the difference between the last number and the first number. On the other hand, for Qn, the the numerator is the difference between the last number and the second to the last number, while the denominator is the difference between the last number and the first number. So for Q1 in this data set, the second number is 7.89, while the first number is 7.84. Then our last number is 8.07. So in Q1, we obtain a value of 0.21739. For Qn, the last number is 8.07, while the second to the last number is 8.02, and our first number is 7.84. So evaluating these values in this equation, the value for Qn is 0.21739. After obtaining the value of Q1 and Qn, we need to find the critical value for Q. So we will use this table. The value for our n is 7, since we do have 7 numbers or 7 data points in our data set. So the critical value of our Q is 0.64. Since Q critical is larger than Q1 and Qn, hence there is no outlier in this data set if we use the Dixon's method. For the Grubbs method, the first thing that we need to do is to obtain the mean and standard deviation of our data set. For the mean, we can obtain the mean by getting the sum of all the data set and dividing it to the number of data points. So our mean is 7.9655714. Then for our standard deviation, we first need for standard deviation, the first thing we need to do for each data point is to find the square of its distance to the mean. So here, this is the square distance of each data points from the mean and their square. After that, we get the sum. Then we divide it to the number of data points and get the square root. So and get the square root, in which we will obtain a standard deviation of 0.073457. After obtaining the mean and standard deviation, we will now use these two equations in order for us to see if there is an outlier in our given data set using the Grubbs test. So for T1, the numerator is the difference between the mean and the first term, while the denominator is the standard deviation. To say for Tn, instead of subtracting getting the difference of the first term, the, getting the difference between the mean and first term, we will get the difference between the first term and the last term. So evaluating 7.96571 minus 7.84 divided by 0.07934. The value for T1 is 1.58445. For Tn, 7.96571 minus 8.07 divided by 0.07934. The value of Tn is 1.31437. Next, we also need to get the critical value. So the value, since we have 7 data points, the value of our n is 7. And in the given problem, the alpha for this data set is 0.01. So here is the critical t value for our data set, which is 2.10. Since T critical is larger than T1 and Tn, hence there is no outlier in the dataset when we use Grubbs test. Problem question number 3 from problem set 1.4. A 2k factorial design was used to determine the equations for the response surface and the problem 1b. The coded levels, and the responses are shown in the table. Determine the coded and encoded equation for the response surface. In order to get the coded form, we will use this following equations. And since we have 4 responses, the value of our n is equals to 4. So for the first term, or beta 0, so for beta 0, or the first term, we first need to get the sum of all the responses before multiplying it to 1/4. The first term that we obtained is 4.0. For the second term, the responses, we multiply it to its corresponding a asterisk value. For example, 5.92 times positive 1. And after that, we will multiply it. We will also multiply it to 1/4, in which we have a 0 value for our second term. For our third term, the same process on how we follow the same process on how we obtain the second term. However, instead of multiplying the values instead of multiplying the responses to its corresponding a asterisk values, we will multiply it to its corresponding b asterisk values. So for our third term, we have a value of 1.20. For the fourth term, we will for our fourth term, we will multiply a asterisk times b asterisk and its corresponding corresponding response. So for before then we will also multiply it to 1 over 4. So we obtain a value of 0.72. Using this equation, the coded form for our given for the given in the problem is r is equals to 4.00 plus 1.20 b asterisk plus 0.72 a asterisk b asterisk. In order to convert this equation to its uncoded form, we first note the relationship between the coded and uncoded values for A and for B. The relationship can be seen through this equation. To obtain CA, we need to get the average of the high level and low level values for factor A. For example, in this, the high value is 8, while the low level value is 2. Getting the average, we have 5. Then for DA, we can find it by getting the difference between the high value and the average. So the high value for factor A is 8, then the average that we obtain from CA is 5. Subtracting, the value of DA is 3. Now, we will substitute these values in this equation. So we got A is equals to 5 plus 3 A asterisk. Then manipulating this equation, we have an equation for A asterisk, which is A over 3 minus 5 over 3. So for B, we will also use the same process in which the equation that we form for B asterisk is B over 3 minus 5 over 3. Then after that, these values, we will substitute it or evaluate it in this equation in order to get the encoded form. Then we perform the necessary arithmetic processes, like if we need to add, then we add in order to simplify our equation. So the encoded form for this problem is r is equals to 4 minus 0.40a plus 0.08 ab.